common part in those companies is that they're all solving something important for the people. So Skype solved communication, TransferWise solved international money transfer, and now at Taxify we are solving transportation. So today I will talk about what is Taxify. Then I will do 2 examples of 2 systems and tell about overall systems, how we are solving. I also will tell about our challenges and opportunities, because usually nobody tells about non-successful stories, but I'm telling about what are the challenges for us also. And I will leave some time for questions and answers also. So going forward, please raise your hand who has used Taxify. Okay, it's around 30–40% from the people. So Taxify is for the client taxi ordering application, and we are calling it 2-click ordering service. So you need to do pretty much 2 clicks to get a taxi to come to you. And here is example from the client app. So this is what is visible for most of the people and for the clients who use the service. Going forward, so I will talk about the system. So one part is what is visible for the clients, but another part is what we actually need to build to support this system. So on this side we have client applications. So we have supporting different platforms, iOS, Android, and Windows Phone. We have also web client. Then we have driver applications, because we need to connect riders with drivers in the best way. So for the drivers we have also both platforms, iOS and Android supported, which they are using every day. Then we have also taxi companies who have joined us, and for them we need to provide a dashboard where they can see how many rides they are doing, which persons are or which drivers are doing the rides, and all kinds of statistics. Also, we have our own back office systems, because we need to see what is going on in the city. We have a lot of statistics, which I will tell about more in detail, and also managing the prices and all different rules. In addition to that, we have support for taxi companies and dispatcher systems. So some people still like to call, and for that we are giving opportunity to call through our systems, but it's actually routed through Taxify. So there are calls coming in through usual phone lines. Dispatchers see the phone number and can route this ride to the appropriate driver. Then we have also driver portal. This is the place where taxi drivers can sign up. And actually, many drivers got their first email with us by signing up. Also, we have business dashboard. So we have corporate clients. This means that if you are part of a company, you can choose as payment method this company, and you don't have to pay in the car. And it's really convenient, because at the end of the month, company gets one bill for all the employees and can pay with one bill this rides for these rides. And also we have one other system, which is button. This is for hotels or for example for library. It's meant that you can go to the receptionist and just do 1 click and taxi is ordered for the client. And what we have to do is connect all these systems through our backend systems. So how have we solved this? So here's the diagram. This is how it looks like. The idea about this is to show that actually it's a lot of small components which are connected with each other. And this is to handle all the complexity and also being able to move fast. So we are not using one big hammer to solve the problem, but many smaller ones. So now I will move on and tell about the services. So we have service-oriented architecture, a lot of small services connected to each other and talking to each other. In the backend, we are using Node.js for the services. And why we are using Node.js is that it's asynchronous. It's very well supported for the real-time applications. It's well scalable. It's also a scripting language, so it's really easy to get it running. You don't need to compile. And it's also supported in all the cloud providers, whether it's Azure or Amazon Web Services or any other provider. So it's well suitable for cloud deployment. One other thing is that it's single-threaded. So it means that it hides all the complexity about thread synchronization, which you get in many other languages and which is the cause for many issues. And as it's single-threaded, it means it can one service can consume maximum one CPU core at a time, and this means you have to think about the scale right away when you develop your services, because you need to likely run many services for the same operation. Now I will move on to one example of a system which we have built. So like I said, we have a marketplace where we have to connect drivers with the clients. So first thing is, in order to connect drivers to clients, we need to know where the drivers are. For that, drivers are sending, or driver applications are sending their location information every second. Every 2 seconds. They are sending their status about their location, GPS coordinates, longitude and latitude. And this means that, of course, there are all the drivers sending to these service. From there on, this is in memory. We keep it in memory. There's no persistence layer for that, because every 2 seconds there is a new coordinate. And this service buffers this and sends every 2 seconds forward to the search service for all the drivers. So if there are thousands of drivers, this is sent everything at once to the search service. And search service is responsible for matching clients to the drivers, basically finding the closest drivers for the client. I will tell more about this very soon. And what client applications are doing, these are connecting to the search service and asking, which are the closest drivers for me? So search service is also in memory, kept in memory. There's no persistence layer. There we use a k-dimensional binary tree for sorting the coordinates for the drivers. And in our case, it's 2-dimensional binary tree. And here, if client application connects, it can get the response about the closest drivers for that client. This would work very well if we would have a like plain field where there are no streets. Because in real streets, actually closest car might not come as the first one, because you have streets and this takes a lot of time. So actually to sort it by the streets or actual distance, we are sending this query about the closest cars. We are sending to the Google distance matrix. And this service gives us back the actual distance by the map to the client. And this is then returned to the client application. And then the client can choose the closest car. We are also showing the estimated time of arrival based on the distance through the streets with that. And then going forward, when you are driving with the client application, so we are showing you the map view and where you are. But as we need to keep the client application battery usage minimum, we are turning off GPS at that time. And for that, client application is actually asking from this service, driver polling service, about the actual coordinates from the driver. Because the usage patterns are very different for the client application and driver application. Client application, we want people to use like very minimal time, 30 seconds, maybe even less, just to order car and get going. On another hand, drivers are using their application for 10 hours a day. So it's totally different pattern. And we are optimizing all the battery usage and data usage for client applications, not for driver applications. And 90% of requests are answered below 4 milliseconds, so it's pretty fast. And this box around here means that these services are actually deployed by geographical location. This is information, this is real-time information which you need mostly for one city only. For example, in Riga, you need Riga drivers and clients from Riga. You're not likely order taxi from Thailand to Riga or some other city. And this means that actually these are, besides the state in the memory, they are stateless services, which means that if the services crash, they will right away restore their state. So nothing bad happens. And for persistent storage, we have a service called tracking. So after the ride, the driver application sends all the coordinates back to our tracking service. This was every 2 seconds coordinates. So we have good information about the actual trip. And I will tell about this later, what we can do with this data actually. And yeah, so from protocols, so we are using only HTTPS protocol. Like I said, with Node.js, everything about HTTP is supported, and that's why we are using this. It's the fastest way to develop for us. Now I'm moving forward to one other system, which is statistics systems. Statistics system. So we are gathering pretty much all the data what we have. And this is one random example of a funnel from different events. And we are using all those funnels to analyze customer behavior and then trying to improve this. From this you can see it's getting pretty much lower with every step, and we are running a lot of this. And what we saw that we are using MySQL as the relational database. We saw that these queries are getting slower and slower. And we knew that sooner or later it's not possible to run those on single machine. It's just getting too slow. So we had to come up with a new solution. This is a bit more detailed example how we were using those databases. So we thought about different ways to solve this problem. Either use Hadoop and MapReduce or do some pre-computing. But this wouldn't work that well for us because we needed real-time queries and a lot of different filters and parameters. For example, grouping by day or hour or month or week, and lots of different filters like looking only at data from a certain city or certain polygon which we have defined, and filtering by all other parameters, like tens of parameters. And going forward, so we needed something familiar also, because most of the engineers are very well used to SQL. We wanted something similar so that they can continue writing queries easily. And also we wanted minimum effort to scale. We didn't want to spend any time scaling the databases. We wanted something off-shelf. And also our motto is to kind of store everything. If you have some data to store, we will store it, even if you don't know how to use it today. And what we came up with was actually moving to Amazon Web Services, and from there Amazon Redshift. So Amazon Redshift is columnar database. It's SQL-like query built on PostgreSQL. It's meant for big data and big data analysis. And what is good part is that they have solved the scaling queries across many machines. So you can choose on how many machines your query run. So for example, your query can run on 5 machines. You just need to provide the partitioning key. How do you partition the data? And our data is mostly very well partitionable. So we can easily pretty much going to the Amazon Web Services portal and choose how many machines we want to run these queries on to get the performance what we want. So in that sense, we have solved this scalability once with this approach. But now the question is, how did we move there? So we had our data in our real-time databases in MySQLs, and we needed to get this to the Amazon Redshift. So first we needed a service which takes the data from current databases and writes them forward. Amazon Redshift is not very well scalable for small updates and inserts. So we needed to buffer this and needed something in between, which takes bigger chunks of data at once and writes them to the Redshift. For that, we used Amazon S3, which is scalable file storage. So we took a bunch of data, wrote to Amazon S3, and from there on, there were bigger chunks. There was another service, what we called Redshift Syncer service, which took the data or bigger chunks from there and then wrote to the Redshift cluster. So this is how we solved the synchronization from current database to the Redshift. In addition to that, we saw that, okay, we have now data in Redshift, so we need to route the queries directly to Redshift from our back office. And for that, we built an API service on Amazon also, Amazon Beanstalk, which is also auto-scalable up and down scale from the services. So also we have solved the scalability, although this service doesn't need a lot of scale. And then back office is directly talking to Amazon API. But going forward, then we saw that, okay, we have data in real-time database, and now we are writing and synchronizing this to Redshift. But there was a lot of data which we didn't need in the real-time database here. So for that, we actually built a new statistics API so that mobile applications are directly writing to that API and then storing this in Amazon S3. And from there on, it gets synchronized to the Redshift. And in Redshift, so we are putting together different kind of data. For example, number of writes or write data, but we don't need always everything there. So actually, we are doing data modification in those Syncer services also. We are only getting the data what we need to Redshift. And mobile apps are writing a lot of like events data or what we analyze from the UI, what is happening on the user interface layer. And these we never need in the real-time database. So this goes directly to Amazon Redshift. Okay, so moving forward. So I talked about service-oriented architecture, that we have service-oriented architecture. There was nice talk about architecture before by Simon. And the question was like how to do that. If you move to microservices, you are creating a lot of complexity, which you need to solve other way. So just moving to microservices doesn't give you benefit. You need to exactly know you are still responsible how you build your services. So our approach has been build services. Whether they are microservices or bigger services, doesn't matter. This is up to us. Build logical services so that services own data and they are closed in that sense that the only way to access is public interface. And same approach we are taking in code. So if the code base for one service is getting too big, you need to separate the accesses to the modules in the code and then split them out to the services. And it's up to us how do we do this, but we are not like just going to microservices, but looking service by service. If it makes sense, we are moving it to a service. If there's no need, we are not moving it. And here is example about the load by different services. So what we can see here is that some patterns by the day are going here. So usually the highest load is starting from the morning until like midnight. Of course, the difference is weekends, where we get high peaks on nights. So this is 13th Friday, and this is Saturday night. And some services get a lot of load, which are accessed by clients directly. Some get less, not so big difference. For one more interesting example, I show New Year's Eve from last year. So what we can see is usual pattern here. Then we can see that no change in some services. Then one service got 5 times higher load. This was actually the same search service what I got, what I described before. So a lot of people tried to search for cars, and actually they did a lot of refreshes because there's just not enough cars available on this day. But interesting to see is like that this one got even double the amount from this service. And what's the reason behind this is that this service actually does 2 calls to this service. It's our one of the user services, so it actually got authentication request and also saving some of the this search results data here. So this got 2 calls. But what is to learn from here is that if you're building service-oriented architecture, you have to think about every call. So because it can have very big effect if one of the services scales and it has dependency to other services, which gets more requests. And it also shows that you can, by services, look at your architecture and scale them differently. You know that, okay, some services you don't need to do anything, and others you need to scale. So next I will talk about what are the challenges and also about what are the opportunities. So one of the challenges is really user interaction design on mobile applications. This is really hard. It sounds simple, but actually when you are testing with people, you get totally different results. Very hard. And from challenges, I will tell and show some examples. What are the hard parts to solve? And we have also like big opportunities with big data. Like I said, we are storing everything, and even if you don't know what to do with this data today. So here is an example of user experience and interaction design. So this screen is the first screen what you see when you open the application. This is where you choose your location where you want to order the car. So basically you are confirming your address where you are. And this has been, this was long time like this, and it's currently also similar. Then we did 2 small changes. And this is the changed screen. So we introduced kind of premium category of cars, and we wanted to, and also we have private drivers in some markets. So not only taxi drivers, but private drivers like ride sharing. So we wanted to introduce car icons for premium cars. And these were more like black-gray cars. So we changed one icon for this category. Also, we changed this text. So before it was confirm address, but then we had it like set pickup or like set your pickup location. The idea was that you don't need to know the address. We can actually order the taxi to just to the point as location, and we wanted to move away from the address and tell to the customers that you can just choose the location. You can be on a field and still car can come for you. And so the question is, what do you think, what happened with this small change? It was pretty much no code change. It was just 2 updates.
People probably would think that the gray cars are unavailable for rent calling.
Okay. Any other ideas?
They were trying to pick up a car, not the placement.
Yeah. Okay, but I will tell what happened. Yeah. So what happened is that first, this text, people were thinking about this, that okay, come pick me up. That this is the final confirmation that now I'm ordering the car. It wasn't anymore about setting your location, but it was like, okay, now the car is gonna come. So they were afraid to press this because now I'm ordering and I don't have the information. So next thing was that, okay, I want to know what are the prices or what cars am I ordering. So they started clicking on those icons. But we have no support for clicking on those icons. So nothing happened. And then they made a realization that yes, these are busy cars or unavailable cars. So 2 small changes, like really big impact. And it didn't impact, by the way, like existing customers. They are used to that. But mostly it was about new customers. But these are like really hardest to grasp really quickly, like what's really going on, or how do you do those changes. Okay, so next I'm moving more to the data. So there is example of usual Tuesdays and Wednesdays in Riga. This graph shows number of rides, number of orders. So here we can see end of month, good weather. It's pretty much flat, the growth vector. Here it's start of month and good weather, a bit of growth or pretty much same. Then we have second week of month, like really high going growth vector, and there was raining a bit. So this has a pretty big impact. Also we can see this is weekend. Also we can see that usually like first or second weekend is the highest because of there is like payday, and this increases the number of rides. Yeah, this affects. But then we had okay, non-stop rain and national holiday in Riga, Independence Day, like really different growths, like three times more. And next comes the weekend from there. So from here we can see that it's like 1 month, usual days, Tuesdays and Wednesdays, but totally different need for the service. Here is, to tell more about this, here is a map of Riga, and this shows the number of orders in logarithmic base. So it means that red ones are much more higher demand areas and blue ones less, and others have pretty much nothing. So we are here, so we can see that it's not that popular place. So for us, the question is how can we predict this? So here is more zoomed out picture. So we can see, this is where most of the action goes, and here is less. So what we need to do is actually know about where the demand is going to happen. So predict demand, like where people are going to order taxis. And we need to know exactly which are the spots where it's going to happen. So here's one other example from Tallinn, what's going on. This is one average day in Tallinn. So you can see like this is the client and this is the driver. So when there is a line, it means driver is either going to pick up that client or driving with the client to the destination. So the lines show that these are connected, client and driver are connected. And the green ones are free cars, available cars. And we can see it's more in that center of city. But what's the problem is that we need to predict where is going to the demand happen. And it's really hard topic. So it depends on a lot of things. It depends on city, it depends on local area. For example, in Spain, you have siestas, so this is different. It doesn't happen in other countries like that. Also, it depends on live road traffic, which we need to take into account, and also like events and campaigns. For example, we are giving out these promo codes here in this event. So when this event is going to end, like there are 350 people, if they need a car right away, it means the demand is growing here. So we need to predict this based on few or some orders, that this is the place where the demand is going to increase, and route some drivers here. And also take a lot of historical data into account, like doing analysis based on last year, same days. So we know the seasonality per day, we know the seasonality by hours, and also a lot of real-time data which is affecting this. And these are the challenges which we are working on. And this is really hard topic. Here I do another example. So the idea is that we are more and more dependent on the maps. We have to do everything based on maps. And here is example of only tunnel in Tallinn. So you can see the black one is GPS coordinates from the driver, and it jumps here. So we think that the car went there, but it actually didn't. So what we have to do is actually correct route. So in this case, it's pretty easy. You have to be pretty fast to jump here, and we got the coordinates from here, so we corrected it like this. All good, nothing special. Here is a bit more complicated example. So this is the start of the trip, and there is tunnel, long tunnel in Prague. And here it's coming on the ground, here also. So what we are doing is we are correcting it as a straight line. So actually we are making the trip shorter for the customer. So customer pays less because we are correcting the route as direct distance. But this is not correct, and it's not good for drivers because they get less money. And also where all estimations of arrival or more complicated areas, we need to solve this by mapping the actual route to the road. And this is one big challenge what we are working on. And here's one example of really screwed up case. So you can see that by GPS data, driver was jumping between here and here, and from here, then from here. So if you're going hiking with your mobile phone to the woods, be prepared to get lost. So never trust GPS. Okay, so this is the summary. So we are operating in 9 countries, and we have service-oriented architecture, 22 systems at the moment. We don't have microservices, although some are smaller ones, but we have more like service-oriented. It doesn't depend what is the size. If it's a service, it's a service. And mostly we have asynchronous real-time systems, and I told about 2 examples of the systems which we solved or how we solved, and also about challenges and opportunities. So we have a lot of opportunities in big data analysis, and more and more getting involved with maps. So actually currently we are doing cooperation with cooperation with some of the universities to get some help from there, because there are like really interesting topics. If you think that we have done like 2 million writes and we have data points for every 2 seconds, you can do a lot of analysis on that and get some really interesting insights out of that. Okay, and I leave time for some questions.
How do you do with user experience testing? Do you track some user data, or just you pick up some customers and make some local testing?
Yeah. Okay. So the question was, how do we do user testing? Whether we do it based on data or something else. So we do it both ways. So we do interaction tests with people who haven't used the application before, and actually we are mostly doing it so that you find a friend and ask him to do something and don't give any help and see how they react. This is the easiest. Of course, it can be done so that you get people to a room and ask them to do something and then record the results. But this gives quite a lot of info. You don't need that many people actually to get good insight. And besides that, so we are tracking all the events what customers do. And based on that, we do changes. Good example is we have these referral codes. So if you invite a friend, you get the free ride. And there were options in the order like Facebook, Twitter, email, something like that. And then we measured like how many are clicked. And then we saw that Twitter was clicked less and give least results. So we changed this. We changed the order based on the popularity, and also we added some other options like SMS, for example. So we are tracking all these and then making adjustment based on that.
You know, you showed that slide where you changed the pattern and the colors of the car. How do you know new customers pressing the gray car?
Yeah, this was only with interaction test, like testing with people who haven't used this. So this we are not tracking. This was only by interaction test. Yes.
As you mentioned, you store everything and then you partition because your data is very easily partitioned. If you don't know how you will use it in the future, you store everything without knowing how you use it, how you partition it.
Then we are just storing it. It just means that the querying is slow.
Okay, so you don't partition it
Before.
in the very beginning.
Yes.
Okay.
Yes. Okay, yes, you were first.
What transport technologies you are using to get those 4 milliseconds to get from driver application back and then also from client application? So you are using REST or something software?
Yeah, so the question was how do we get, what technology do we use to get this below or 4 millisecond answer times? So to be clear, this 4 milliseconds is measured from the service layer. And as this is in-memory data structure, it's really fast. So we have no storage layer to access. That's why it's so fast. When it comes to the actual time from the application to our servers, then this of course is much bigger, because this depends on mobile connectivity and what type of mobile connectivity you have and where you are. In some cases you have like no connection. So
you're sending binary data or REST or?
Yes, sorry, yeah, we are using only like REST, only HTTP based. Okay.
How do you hire developers? I mean, if someone comes to you and says, hey, I'm a great developer, what's your procedure for telling he's going to perform well? Do you have any shortcuts to go through that?
As well, how big is your team?
Yeah, so the question was like how do we hire developers and how big is our team? So our team is pretty small, it's around 10 people, 10 engineers, and both Taxify is 30 people. But how do we hire engineers? So we are doing interviews and usually like coding tasks, like small coding tasks. The coding tasks are not meant to be so that you need to solve those really well and you need to know everything. It's more about getting the basic stuff and see how the person thinks. So it's pretty standard to compare with other companies also. Main thing is to see how the person thinks and how he can in real life solve the problem.
Do you use more theoretical questions or more practical? I mean, people sometimes get worried when they sit down for a group. So you ask a theory like, write me a 5-minute review, right? Well, just not do it well because you're worried that they will do that in quite a lot of time.
Yeah, so usually what I've done is actually a pretty simple problem. So you can, good example is about reversing a string. So you can do it in many ways, but you can discuss about this and see if there are like basic mistakes done. So it's more about seeing how person thinks. It's less about the result. There was one question from the back there. Yeah. Not anymore. Let's take some minutes.
Are you doing any A/B testing?
Yeah, so the question, are we doing any A/B testing? Yes, we are doing, but not too much. Not because we don't want to do, but just because setting up an A/B test and actually looking at the results correct way, it takes time. And then you need to make sure that actually this was the cause for the effect. So we would like to do more, and we will be doing more.
Since we're a small team and you showed us very nice charts from the data that you're getting, I would like to ask, is it a system that you wrote yourself or you're using something that's already done for drawing the charts?
So the question was like, we are a small team, and then what do we use to, was it about drawing the charts or?
Yeah, like that system that takes the data and draws the charts for you. Is it something that's open source or it's something that you wrote yourself?
Yeah, this is some open source. It's not done by yes. Or actually, did you mean the statistics table? Sorry, yeah, the statistic table. This is our own. This is written by us. But the server statistics graphs, these are open source. Yeah. Okay. Last question, I think. Yeah.
You mentioned that correcting the driver paths is a big trouble because if you get it wrong, then the pay is not correct. But in my experience, taxis have their own system in their taxi which measures the distance. So how is that affecting them if you're getting your data wrong?
Yeah. So the question was that how do we correct the route, and if we get it wrong, what happens, and also because taxis have their own taximeters, so why do we do that? So in some countries like Estonia and Latvia, there are taximeters, and this is required by law to use those. But in many other countries, there are no taximeters, and there we are using our application to calculate the price and route and everything. So it's replacing the taximeter. And it also gives ability for really good features, like we can dynamically change the price, which you can't do with taximeter. So I think in time it will just go away, and just devices and apps will replace this fully. Okay, I think that was last one. Thank you.